Okay, so we wanted to cover the physics of monopoles, instantons, the electromagnetic duality, maybe dip our toes into some Seiberg-Witten theory eventually. But before any of that, we should understand monopoles in electromagnetism, and that's what we'll do today. So start with Dirac's monopole. And the basic question here is how to take the Yang-Mills equations as we know them and what the necessary modifications are, figure out what the necessary modifications are to have a source, a magnetic source, in addition to an electric one. But first, let's remind ourselves of how to package the electric and magnetic fields into the electromagnetic field strength. I think that would help. So we know that the electric and magnetic fields, the way we normally think about them, are vector fields. But we could just use the metric and convert them to forms, right? To one forms, EI and B sub I.
Right.
And what we want to do is actually take the electric field and define a one form with it, but dualize the one form for the magnetic field and define a two form the way I have here. I mean, I should be a little bit careful because this is epsilon ijk of just space, right? Not space-time. But still, this is what I'll define the magnetic field two form as. I mean, it's just a component notation. We could just recover what it means by looking at the full star and figuring it out. But this is the basic idea behind defining the electromagnetic field strength. This is how you define the electric and magnetic fields. So you have a component of F along the time direction, right? And that's E wedge dt. Note that that's actually EI dxi wedge dt. So this is actually going to be a two form. And then we just add B. B is already a two form. And note that you can recover the components by just looking at the individual, like, F0i and taking the spatial Hodge dual of F, right? So epsilon F is B. And now what we want to do is try and understand what operation swaps electric and magnetic fields. But before that, let's just remember how the Hodge star works, because it's going to be related to the Hodge star, as you can imagine. So the Hodge star acting on two forms will give you another two form in 4 dimensions, right? And the definition is just what I have here for dx mu with dx neo, the basis one, the wedge of the basis one forms. If I take the star, then I get another two form with the epsilon symbol involved. And then the star of dt with dxi, where one of the dx's is t, is going to be given by this epsilon 0 ijk dxj with dxk, which is the same as the spatial epsilon tensor dxj with dxk. And then recall that in Lorentzian signature, if you take the Hodge star twice, you get -1, right? In Euclidean signature, you get +1, which is why you have, self-dual and anti-self-dual. Connections transform, field strength transforming is star F equals F or star F equals -F. Here it's -1, so you actually have complex self-dual and anti-self-dual parts if you wanted to do the split. But we're not going to do that. Just the fact that it's a star squares to -1 means that if I took the star of now this epsilon ijk dxj with dxk, remember that's what sits with the magnetic field, right? That's how you define the magnetic field two form. You get minus dt with dx, right? So these two forms are swapped under the star operation, which then tells us that if you took the Hodge star of the field strength, then you're very simply exchanging electric and magnetic fields. So the electromagnetic duality, if it exists, right, if it manifests, should be a duality undertaking the Hodge star of the field strength tensor. So you see, if I had vacuum, right, no sources, then I trivially have this symmetry because df would be 0 and d star f would be 0. And so it doesn't matter. I take the star, the same thing is true. Now, why? So that's basically the statement I have on the slide. Df is 0. I replace it with star f. It's still uh, exact. Well, closed. Sorry, not exact. Now, what happens when I have an electric charge? If I have an electric charge, then d star f will equal j, the source one form for the current one form, basically. But then df will still be 0, right? That's the Bianchi identity.
Right. Okay.
So
yeah.
together, you basically don't have the duality, right? So in order to have some kind of duality, you need to introduce a source also for the magnetic field. And that's the idea of having magnetic monopoles. You need also for star df to equal k, right? So star d star f is j, right? Or d star f is star j, if you wanted to put it that way. And you see, you need a duality not just under f going to minus star f, but j going to minus k. So you need to swap the charges and the monopoles. Right? But now, what was df equals 0 useful for? Well, if df is 0, then locally f can be written as dA, where A is the gauge potential. But if df is no longer 0, then we have to think, right? So what, yeah, the real cost to introducing monopoles is you don't have a globally defined vector potential anymore, right? You can't. So let's restrict our attention to the simplest source, right? It's just a point magnetic charge at the origin. And since it's a localized source, you can locally define the gauge fields, right? Because df is not equal to 0 only at the origin. So this is the idea of having some patchwise connection, right? So it's a connection that's only locally defined. So here I have the explicit form of the connection that sources, that's consistent with the field equations with the point magnetic source at the origin. And as you'll notice, this connection is defined everywhere except for an axis. So the field strength is localized at a point. But you see, the connection can't just be localized at a point. And why is that? Can you guys see why?
I mean, it's the nature of the connection itself, right? Like,
Well, it's really more, I mean, it's simpler than that. Like it's okay, so it's like saying if I took the integral
hmm,
over a surface,
hmm,
two-dimensional surface
hmm,
of B,
hmm,
the magnetic field two form,
hmm,
I get some right-hand side.
right,
But then if B is okay, so B is really like star F, right? And if
right,
star F is given by D something,
hmm,
then that something is going to be integrated over only the boundary of that. It's going to be integrated over like some lower dimensional
right, okay, mm-hmm.
surface, right?
Yeah,
So that's the sense in which you end up having okay. So let's do this more slowly. So F has a point source, right? So F is sourced by just a point, which means that if I integrated F over a surface, right,
mm-hmm. Mm-hmm.
then it'll give me something non-zero because the surface contracts and catches the point
Yeah,
source.
yeah,
A, however, is only being integrated over
the boundary.
a one-dimensional
Yeah,
loop.
yeah,
It had, if it was just a point where it wasn't defined, then I could close the loop, right? I would miss it.
right, right,
I would get a zero result for the integral.
right,
For it to be non-zero, there has to be some kind of a line, right?
Right.
Because then the intersection number will be non-zero.
Right.
And that's why the gauge field is defined everywhere except for an axis, like, half an axis, basically. It's half the z-axis. If you meditate on the forms of these, on these one forms, you'll notice.
Right.
Now, how would you go from one connection to another? Normally, you would say, there should be a gauge transformation.
Mm-hmm.
The answer is the same here. There is a gauge transformation, but it's a singular gauge transformation, right? Because you see, it just is given by d of phi, and phi is an angle. This is not
Yeah.
continuous, right? And so that's the issue with chi, that it's a discontinuous gauge transformation. And this is going to lead to very interesting physics. And it will actually touch on what we covered before with Aharonov-Bohm phases.
Oh.
So one thing to notice is that the magnetic monopole has the same field as the end of like a semi-infinitely long solenoid.
Yeah.
But it's also going to be infinitely thin, right? Like it's only the end of the solenoid that has the same field as the monopole,
Yeah.
not sort of the
It
rest of it.
just like it's just like saying like I have a magnet that has not the north and the south pole infinitely far apart, and then I'm just locally
Yeah,
observing the one of the two poles.
Yeah.
exactly. It's like you send the other pole off to infinity or
Yeah.
something. But now you have to get rid of the magnet also. That's another
Yeah.
that's another requirement. But you see, the thing about a solenoid
You
is
don't
that
you don't need to address that problem because it's only from the top. Yeah.
yeah, well, that's just the field though. Now the issue with the solenoid is that a wave function will detect the field even if it doesn't interact with, you see, because of the Aharonov-Bohm phase, you're going to have an issue, right?
Right.
Like the wave function of a charged particle will know about the solenoid
Yeah.
unless the Aharonov-Bohm phase is trivial. So what you need in order to make this intuition concrete is literally an infinitely long thin solenoid, right? With the monopole at the end. But it's defined such that the Aharonov-Bohm phase, right, around the solenoid is trivial, meaning it's a global phase, like it's some integer multiple of 2 pi.
Right.
And that gives you Dirac's quantization condition, which tells you what happens when you take a charged particle around a monopole, right? The effect is going to be that of getting an Aharonov-Bohm phase with respect to this trivial gauge, this singular gauge transformation that we discussed, right? And that it's going to take the form of qg over 2 pi times phi. And now there's different ways to think about it, but the single valuedness of the wave function or gauge invariance really means that qg is 2 pi n, where n is an integer. And that's Dirac's quantization condition. So now we've discussed, okay, and that's really interesting, right? But there's more you can actually tell about monopoles. So far we've discussed a charged particle in the presence of a monopole. But in truth, you can have monopoles that have electric charge also. So objects that have both magnetic and electric charges, and these are called dyons. And to study their wave functions and the phases that they pick up, it's actually better to think in terms of the quantization of angular momentum. So we'll try and rederive the expression that we just encountered through the quantization of angular momentum. And this is just a fun exercise. It's something that you can, work out if you put in the effort. So remember that for the electromagnetic field, the angular momentum is given by the following formula, like R times R cross E cross B, where E cross B is the Poynting vector. And remember that B is now given by a formula for a static source, right? The static monopole at the origin. And so you're left with this triple cross product, or this double cross product formula. And you could just work out what the effect of having two cross products is, and you'll get the result on the right-hand side. And what you want to show is that in components, it actually equals this interesting integral. Right? This integral of E contracted with the derivative of the normal vector. Why? Because it'll give you a surface term that you can drop minus essentially Gauss's law. Right? And the nice thing about Gauss's law is you know what it evaluates to. It evaluates to Q, right? So from the quantization of angular momentum, now you can regain Dirac's quantization condition. And now the exercise, the homework for you guys is do this with dion, right? With just two dions. Basically, you have like E equals E1 plus E2 and B equals B1 plus B2. And you run the whole exercise and you'll recover something interesting called the Schwinger-Zwanziger quantization condition, which relates an interesting combination of charges and electric and magnetic charges. Specifically, it looks like this. And I've taken this from Preskill's notes. Really, how you can see that arising, another way to think about it is by doing like a double, like a braid, essentially. Like you take one dion around the other, and then you take the other dion around the first, but in opposite directions. And look at the Aharonov-Bohm phases that you pick up. And you'll get this condition again. I mean, this is a clever argument, but I think that the angular momentum exercise will give you a better, handle of it. Now, preparing for this episode led me to some interesting articles, like this paper by Witten, which is pretty short and actually pretty readable. And you realize that there's some implications of this quantization condition. It actually tells you something about the difference between the electric charges of two monopoles. So the basic idea
quantized.
Oh, wow. Yeah, exactly. So the idea really is to say, the minimum possible magnetic charge is 2 pi over E. Okay. And say you had two electric charges Q and Q prime, and then apply this quantization condition we saw before.
Right.
And you basically find that the difference between any two charges has to be quantized in units of the fundamental electric charge. So that in some sense, quantization of charge differences comes from there being monopoles. So once you've swallowed this interesting fact, we can then look at adding an additional condition that will actually tell us that electric charge has to be strictly quantized. And that's CP conservation. So charge conjugation and parity. So under charge conjugation and parity transformation, Q goes to minus Q, but the magnetic charge, 2 pi over E, stays the same. Remember that electric and magnetic fields behave differently under parity, right? So one is a vector, the other is a pseudo vector. And also, if CP is conserved, then you realize that the net effect on the charges has to be what we have here, right? Cool. So now let's apply the quantization condition on Q 2 pi over E and minus Q 2 pi over E. What are you going to get? 4 pi Q over E, right? And that has to be 2 pi, that has to equal 2 pi n. And that requires Q to be an integer multiple of E, or a half integer multiple of E, which is a really neat argument, right? So in some sense, you need magnetic charges in order to realize that electric charges are quantized.
Wow.
But of course, we're talking about dyons of charge e theta over 2 pi. So what could that mean, right? And so the theta here comes from a theta term in the electromagnetic action. So what would happen if you added to Yang-Mills theory a so-called theta term, which violates CP? So you have F wedge star F. That's your Yang-Mills action. But F wedge F is also an equally good four form that you can integrate, right? So theta integral F wedge F is called a theta term. And when you break it down in terms of electric and magnetic fields, it's like adding E dot B to the action. This is what you call axial electrodynamics. Well, if theta is a function, then it's called axial electrodynamics. So here, Britton does something very neat. Basically, he invokes like old quantum mechanics, which is a weird thing to do, but I mean, let's entertain him. So recall that there's this Boris-Armorfield quantization condition that says that along constant energy surfaces in phase space, if you took an integral of p dq, then it'll be some multiple of h bar, right? Oh, so semi-classical quantum mechanics essentially is classical mechanics on such orbits, right? Now, what he wants to do is apply this to the case of charge, like a charge source in the presence of an electromagnetic field. So now here's a little exercise for you guys. Why is that requirement that I've written as a Bohr-Sommerfeld condition equivalent to writing T times I plus E equals 2 pi n, where I is the action per unit time and E is the energy?
I'm taking a stab in the dark over here. Is it something related to the phase of?
No, it's just as simple as saying, like, I want to rewrite the condition that I have over here, that P, like the integral P dq is multiple of h bar. But instead, what I'll do is I'll write the action. So I want to write it in terms of the action, right?
Oh, okay.
So the action is going to be T times I, but I don't want the whole action. So action is P dq minus h dt. So I want to add back the h dt part, and that's just going to be ET, right?
Right.
So that's how I get this rewritten condition.
Got it. Okay.
And so he says, okay, in the absence of CP violation, you basically get the following condition, right? If you have no CP violation, then you have I plus E being CQ squared, and that the period is going to be proportional to 1 over Q. And then imposing that condition gives you Q being an integer multiple of the electric charge. But with CP violation, you're going to have an additional term, as we discussed, which is proportional to theta.
Right.
And that's going to change the condition where now you no longer have the quantization of the electric charge, but you have this theta term, this theta E over 2 pi. This is called the Witten effect. We'll come back to this eventually.
Does that, is it just a way of somehow linking together the electric and magnetic charges and saying that one kind of flows or transforms into another? I mean,
Which?
like so when you have the theta term right here, is it just another way of saying the electric, like you need to have both electric and magnetic charges, and then one kind of flows into another or something? Like, is that the additional term that we're looking for, condition that we're looking for?
I wouldn't say that, because in some sense, even without that term, you have a relation between electric and magnetic charges, right? Which is this relation. Basically, I mean, it has many effects. So the question is, what's one of the simplest effects it has. And the simplest effect it has is that it just ruins our very nice quantization of charge condition. Its full implications are quite rich and interesting. I mean, you can actually promote theta to a field, and it's called the axion. And normally you don't discuss the axion. So this would be an electromagnetic axion. Usually you discuss the axion for like non-abelian gauge theory in the context of the strong force. And it's a dark matter candidate. There's all kinds of interesting physics behind it. But at base level, what it does is it kind of ruins the quantization of electric charge. Basically enters, well, in other words, theta enters the value of the electric charge in this way. So yeah, I mean, maybe there's another way to look at it, but you know, could, yeah, sort that out later. So far we've mostly discussed the Dirac monopole, which is interesting, but the drawback is that you had to put it in by hand. It requires some singular gauge configuration. It's just like, what if this happened? Whereas, you know, if you have a monopole in nature, you'd expect that there's some mechanism behind which, behind sourcing it, right? Like, we know that there's an electron field, and that sources electric charges, right? So from where do magnetic charges come from, really? So what I mean by this analogy is, if I started with electromagnetism and then I was just looking at point sources, then yeah, I would write down something that looked very similar to what I had for the magnetic field, right? Like E equals Q over R squared, R cubed times R hat, or something like that, right? But I actually know where that source came from. It came from the coupling to a Dirac field, right? The electron field, which has like a current, and the current is given by like psi bar gamma mu of psi, and that I have some solution to the Dirac equations that looks like a point source in electromagnetism. And the idea behind the Topf-Polyakov monopole is to discover what the physics of the source for the monopole really is in the electric case. So it's like, what field configurations actually gives you magnetic charge? And it turns out that for that, you actually need look no further than the Georgi-Glashow model, which is the bosonic part of the Georgi-Glashow model, right? So Higgs field, SU2 Higgs, coupled to an SU2 gauge theory. And since we're talking about electric charges and magnetic charges, what do we need? We need symmetry breaking from SU2 down to U1, right? And so the idea is, in the broken phase, I effectively have an electromagnetic field. And out of this electromagnetic field, I'll find configurations that look like monopoles, but really they're just interesting configurations of the scalar, of the Higgs. And that's the Topf-Polyakov monopole. So we now have a choice. We could go into that, spend a bit of time on that, or we could save it for next time. What do you guys think?
Yeah, I'd definitely like to go into it, but I guess for the sake of continuity, we can continue and come back to that, I guess, because yeah, I need some clarification there, I guess.
Sure. So I mean, if you have any questions, let me know. We could just discuss what we've gone over so far.
Okay. No, yeah, could you go back to the Topf-Polyakov
okay.
monopole? Yeah. Yeah, so how does it come into the theory, the monopoles?
Right. So I mean, that's essentially the question, right? Like even before, like when I showed you the Dirac monopole,
right?
I just wrote some classical source.
Yeah.
How do I know where it came from, right?
Right.
So the idea of the Topf-Polyakov monopole is to actually find out It gives you an answer to that question.
Right.
But it doesn't work by just coupling electromagnetism to some fields. In fact, you start with an SU2 theory, right?
Mm-hmm.
But with a Higgs field, right? The potential that looks like a Mexican hat.
Yeah. Yeah.
And so when you're in the symmetry broken phase,
Mm.
what's going to happen is that you're going to have a residual, you're going to have U1 symmetry.
Right.
And what's more, you're going to have a U1 gauge field,
Right.
right?
Mm-hmm.
And this U1 gauge field will have monopoles and
Okay.
charges. But if you really think about what those monopoles are, you'll discover that they're just configurations of phi, the Higgs field.
Right. Right. Mm. Okay.
And there's a lot of interesting things you'll find. You'll find that there's no need for the configuration to actually be singular. It's not going to have any singularity. Far from the source, it'll look like a monopole.
Mm-hmm.
But as you zoom in, you'll actually discover that there's a core, which is just a scalar field. Like there's just some finite energy configuration of the scalar field.
I see.
And you're going to discover that the monopole charge will be given by Brewer degree, which we discussed when we were discussing vortices. It's just going to be like the higher dimensional generalization of a vortex.
Oh, okay.
And
that sounds interesting.
yeah, that it's going to be topological.
That's nice. Okay. Let's see. Yeah, the rest was pretty straightforward, I would say.
Mm-hmm.
Mm-hmm. Yeah.
Cool. So we'll conclude for now.
Mm-hmm.
And yeah, look forward to
Did
next
you
time.
have any questions or
Yeah.
anything?
What about Pratyut?
Not really.
Okay. Okay. I guess we can continue from here next time. Yep.
Great.